Welcome back to lecture 2. We are about to start the second lecture of module 1, and this is primarily on linked list representation. So I'll assume that the basic introduction to stacks and queues that we did using arrays are sort of clear. You have read it up in the notes which was supplied. However, if there are doubts, you can always ask me when I'll give you a chance to ask questions. So I'll start with the linked list representation thing. So basically I have to introduce to you the basic ideas of a linked list. For those who know, it will be a small repetition, okay? But I am assuming no knowledge right now. So there are few issues to this representation. This is not an array. Okay, so how do I represent? Suppose there are 3 elements in a list. Without any language, we'll represent it as something like this. Okay, so we create a box with 2 compartments. In one we'll put a value. So I'm going to create a list with values say 20, 2 and -5. 3 values. So the first box will get the value 20. Okay. The second box which I will create should get the value 2, and the third box will get the value -5. Okay. However, we need to connect them, right? The first element is 20, the next element is 2. So conceptually or visually we connect them by drawing an arrow from the second compartment of box 1 to the first compartment of box. Similarly, since -5 follows 2, I will draw an arrow like this. Since the first element is 20, I will call this as my list. So I'll give it a name. This is what conceptually a linked list comprises of. So let me summarize. If you have only single values, then any box of the linked list has 2 compartments. One is the value. This is for every box that I'm going to create visually. And the second part basically is a link to the next element. Somehow it links to the next element. Okay. So what is the advantage of a linked list? The primary advantage of a linked list is that it is dynamic. I don't have to guess how many elements this list will have. It is dynamic in nature. So to observe now that if I want to put it in a programming language framework, I need certain features. And those features are what I have put out on my first slide, which talks about a pointer data type and operations, which I'll soon begin. A reference data type, which is typically only present in C++, so I will introduce it. If you do not know, do not worry, it's my job to explain that to you. And then, so the first 3-4 bullets that you see, pointer data type and operations, reference data type and use, class and template functions, these are the bread and butter features of C++ which will help us create and manipulate our links. Okay, so now what I'm going to cover, I will move away from this. We'll cover the materials of slide 2, then slide 3, slide 4, slide 5, 6, 7. So basically everything about pointer arithmetic. Okay, so instead of doing it here, I'll do it like this. So I'll come back to slide 11. So pointers are a world by themselves. Okay, and they essentially deal with the world of, I will call it addresses, memory addresses. So some basic stuff which probably you already know. Whenever you declare any entity, for example, let's say I declare int x equals 25, semicolon. This is a valid declaration in both C and C++. So let's see what have we done in order to introduce this variable called x. Okay. So these are the various attributes of objects or variables. The first attribute of a declaration is first, of course, its name. So I'll write that. In this case, the name is X, as you know, as you can see. The second attribute is what is the data type. Now data type is what appears before X and therefore it is int. Okay. The third is the value, which I'll use the word R value, the read value. Okay. The value is what is assigned to X, in which case this is 25. How many bytes does this variable value occupy? Size in bytes. On my machine, integers are given 4 bytes, so this is a 4 byte long entity. So these are all various properties or attributes of X. The fifth one, which I'm going to introduce you now, the basic purpose is where in location, which is memory, is X placed. Where in the memory? It's a huge RAM, somewhere it is placed. So this is called an L value or the location value, address. This is normally not seen. I don't know what is the address because I've said int X equals 25. The other 4 attributes are known. Okay, so what happens is, if you want to look at it in more greater detail, here is the name X, which I'm writing above the box. The value is 25, I'm putting inside the box. The type is int, I'm writing below the box. The size is 4 bytes. The first 4 attributes I'm writing out here. But what is not obvious is where is X located. So there is an address. Every memory is addressable by bytes. For simplicity, I'll assume it is stored at 1000 byte. Assume in memory it is at the 1000 byte. Then its L value is basically 1000 and all the 5 attributes are now clear. So who assigns this L value? Typically the compiler does the preliminary job, but final job is done by the operating system. So for our understanding, we should understand that every object that you introduce in a program, whether it's a character, a string, an integer, an array, whatever, has one address associated with it, and that is given by the system, the underlying system, and there is a way to get this entity. So now my rest of the discussion is on L values of objects, which are basically also, we'll use the word pointers. So the first thing that you need to know, when you introduce any object, you have a special operator called the ampersand operator, which gives you the address of X. Variable, object, whatever you want to call it. Okay. So for example, if I write int X equals 5 in C++, in C++ I'll use cout to display the value. I can say give me the value of X, it will give it to me. I can put some space to separate out, and then I can ask what is ampersand X, and it will also tell you the value of ampersand X. What is the L value or the address of X? If you are familiar, you already know. If you do not, memory is typically written in hexadecimal base. Okay? Base 16, not base 10, not base 2, base 16. So these numbers are represented with 0x followed by some characters, which is that. So I will not get into this, but basically if you know how to interpret a hexadecimal number, then the address is shown by the system to you if you do ampersand of X. So ampersand of X is an important operator. So this is given an object S, I can know its L value. How do I introduce an element which is a address? Okay. The language people will say, how do you create data type for addresses? I want to only play with addresses. So if you want to create an address like data type, this is how the language allows you. take any type T, put a star and give some name, ABC, whatever you want. So this is the data type, some T, I have not shown you, it could be int, it could be char, it could be anything else, some data type. This star stands for an address, or we actually call it a pointer. So this is the basic. So I need ampersand to get the L value of an object. To create an address like entity, an object, I need to do T star. Now what I'll do is, I'll go back to slide 11 and I'll try and explain whatever I have it here. The first declaration is int I equals 0. This creates a variable I of type integer and it puts the value 0 into it. This you know, so I am not going to explain. Okay, let's take the next one. I'll write it here so that I can explain all of them in slow motion. Int star IP I have written equal to ampersand I. I'll explain this. Then I will do the next declaration, which is int k equals IP. I'll explain that. And let me take the next one also and try and explain, which is unsigned int star UIP equals IP. Okay, and then I can do the rest. So look at the first one, int star IP equal to ampersand I. Firstly, how do you read it? What does the whole thing mean? So let me do it slow motion again. Here is it, int star IP equals ampersand I. So I'll start reading this left to the assignment operator in a right to left manner, in the reverse order. So how do I read it? I read it as IP, which you can see. When it comes to star, I will say is a pointer. Okay, star is replaced by is a pointer to int. This is how I read it as. So what have we said IP is? IP is an address of an integer variable. It also means the same. Is basically an address for integers, of an integer. So if any box has an integer, its address can be taken as int star. Okay, this is the left hand side. So what is the type of left hand side? Type of the LHS of this expression is int star, or in other words, everything to the left of IP. To the left of IP is, this is IP, ignore it, take everything to the left for it, this is the type. This is the type of the left hand side or type of IP. Now look at the type of RHS. The RHS has a variable I whose type is int, and when you take ampersand I, basically you get an address of an integer, address of I. In other words, you can also call it as int star because it's an address of integer. So at this point, the compiler checks for us that LHS is int star because IP is int star, RHS ampersand I is int star, and therefore it's a valid assignment. It goes. What is the effect? The effect is like this. Suppose there was an I which had a value of 10, and suppose the address of I was 5000. Suppose, okay, I'm assuming. What happens after the first statement goes through? Creates yet another box called IP. The content of IP is address of I, which is 5000. Okay, now you can see the differences. R value of I is 10. R value of IP is an address. The content of IP is an address, 5000. The L value of I is 5000. The address where I is stored. What is the L value of IP? I don't know. Maybe it is 6000. Somewhere in memory it is stored. But it's definitely not 5000. It's some other address. The type of I is int, whereas the type of IP is int star. So you should be able to, if you are dealing with such entities for the first time, given a declaration, create this box mentally and check whether it is okay or not. So if you look at the next assignment statement, which is int k equals IP, this also type checks. So on the left hand side I have k whose type is int. So this is the type of the left hand side. On the right hand side I have IP whose type from the previous statement is int star. So int and int star, they don't marry well. You can't take an integer and an address and put them together. So an object and address are coming from different words. So this is invalid and it's a compiler error. So why is the error? Because we did a type and we observed an integer value has been given an address which it is not allowed. An integer variable should take only integer values. Okay, so instead of explaining all, which will take a lot of time, I'll go to this statement, somewhat intimidating, but actually is fairly simple, which is this int double star IP3 equals ampersand IP. So here is the statement, int double star IP3 equals ampersand IP and semicolon. So let me read this slowly. What is the left hand side saying? Left hand side is declaring a name is IP3. The type of IP3 is what appears to the left of it, which is int star star. So how do I do it? I'll draw some boxes. So there is somewhere in the memory a box whose name is IP3. The value that is given I don't yet see because I have not processed the right hand side. I'm only processing the left hand side. What can this contain? So what IP3 can contain is, if I now break it up, something which is star of int star. So which means it contains address of something. So I'll draw a box. It has address of something. And that something is basically an int star. Okay, so star means an address, so I go to put a link somewhere in memory, but this flow itself is an int star. So this is how the arrows can be drawn. The compiler figure out, and a reader of the program should also figure out that what IP3 contains is an address, which itself is an address, and the final object is an integer. This is what its type is. Its type is int star star. Now let us go and process the right hand side. So I should give you what is IP, which was declared earlier. It so turns out that IP was declared as int star IP equals ampersand I. Okay? And I was declared as int I equals 0. So I have to connect all of them. Because IP in its declaration uses I, and this fellow uses address of I. Start drawing the boxes. If this is I, R value is 0, let's say the L value is 2000, the address of I. So I have taken care of this. When I do an IP, this is I. Let me write on the right of the box. IP is an address of integer and is given the address of I in particular. Okay, the address here is fixed, which is 2000. So I put it there because of the right hand side. And let me assume this is 4000. What is 4000? The location value of IP, where IP is stored. But what is stored in IP is 2000. I processed this also. Now observe what is this fellow saying. He is saying that IP3 equals star star int, which is the declaration, but it holds the address of IP. And what is the address of IP? Address of IP is 4000. This is the L value, the address. So basically this says you put 4000 in here. And now you can see once I put 4000 in there, you know what is there in 4000. So this is 4000. The content of 4000 we already know is nothing but 2000. And we know what is the content of 2000. That happens to be 0. So this whole chain of things are established once this whole assignment statement goes through. And why does it go through? Because again, let's go slowly. The type of IP is int star, it's already an address, and if you take the address of this, you get the address of int star, which is int double star. So RHS type is int double star, LHS type is int double star, the type matches, the assignment is proper, and hence this whole chain of things are created. Now coming back to slide 11. Okay, I'm going to skip. Many of these are illegal. You should be able to work out and see why they are illegal later. Let me move on to say that we have introduced two operators, ampersand and star, created objects which are address objects or int star star kind of objects. We declared them and we initialized. This is required to create linked lists. This is only a machinery of C++, the pointer world that we have got slightly introduced to. Great. So let me go on from slide 11. I'll give you a break for asking questions at around, let's say, 2:45, so 15 minutes from now. So remaining slides, you will see that in slow motion I have tried to introduce what I said here quickly, which is how to declare a variable, how to extract its type, okay, do same thing for LHS, RHS, and then do a type checking and figure out what the compiler does. Okay, the next thing which I am going to introduce to you is a reference type in C++. It is known for its similarity with pointers and also well known for its differences. So this is a new type if you have not done C++ before. Okay, so I am going to do on my whiteboard, or basically my pen and pages, with a pen, and then I will switch back to my slides when the time comes. So what is a reference type? Okay, this is, I have to do it in very short, so I have less time. You should read up a C++ book, any standard book, to figure out how people do it. So I'm going to use the pointer way. How to declare such an object is first thing. First is to declare, okay, and then of course is how to use it. So this is how you declare a reference type object. So you write something like int and I, okay, and then I'm going to do something equals some j, and let's say int j equals 15. So about j I don't have to explain, it's an integer object initialized to 15, you all well know about it. It's only I have to explain about this int I equals j, which is my first use in this course of a reference type object. So what have we done here? If I again draw my boxes, I've introduced a new name called I. Its type is not int star, but int and, as to the left of I whatever stacks. Okay. There was already a j out here, so I'll draw the j box also. J had the value 15, so I can write here. J of course has an L value, let's say 100,000. I also has an L value, has to have a place in memory, let's say it is 2000. Now I'm not going to show you what is in I, because that is the mystery. Now suppose after this in C++, I'll use C++, suppose I do what is Cout less than j, and then less than, I'll put some blank, I less than enter. In C++ this says give me the value of j and give me the value of I. The value of j is 15, so I expect 15 to be displayed, which it will indeed do. And what does it do for I? You will observe that the value placed is also 50, okay, which is same as the value of j. Now let me do something. Let me change the value of j. So I do j plus plus, okay, and then I pull out this C statement again, okay, reuse it here, insert it here. Since we have done j plus plus, very clearly in the box j, the value of 15 has moved to 16. Of course, I have not told you what is in I. I'm still not telling you. But if you do this, execute the statement after this change, you observe that I value is become 16, and so is the value of j. Okay, so this is I, this is j first, followed by I. So I'm asking you to believe me that j and I are sort of tied together. Whatever you do to j, I seems to reflect the same thing. Okay, but note down that j is not a copy of I. In the sense that if I change the value of j, then I also changes. You are not copying, it's not j equal to I. No, it's something different. So let me now give you the mystery as to how that happens for a reference type variable. So a reference type variable, we use the word alias. So we create a reference type object, it's an alias of an original object. You have to be alias of someone. So alias of the object of which is it's the reference. Okay, we are going to celebrate Teachers' Day in a short while. Okay, but when we say Teachers Day, we have, in some sense, we refer to somebody which is Dr. Sarvapalli Radhakrishnan. So when we say Pandit Ji, okay, these are all aliases. There may be many Pandit Jis, but without any context is typically Pandit Jawaharlal Nehru and so on. It's the same thing in with terms with aliases. If you say Netaji, despite thousands of Netajis, it's still Subhash Chandra Bose and so on. Okay, so we are familiar in real life with this concept of aliases. So if you use an alias, this is an alias. There must be an original to which it is tied. This is an alias and so on. So alias and the original go together. So when I do, in other words, int and I equals j, I've changed the roles, and let's say int j equals 10, then this I is an alias of j. Okay, what is I? Alias of j. So let me know, now go and give you the secret inside. So this is j, the value is 10. Okay, and let's say j's address is 1000. So here is a new object created I, whose type is int and, it's a reference. And you cannot create a reference without giving the alias of what it is an alias. In other words, int ampersand I semicolon is an error. You cannot create an alias without telling me who is the original object. Okay, so this is not allowed. You must assign it to an object. Okay, fine. Now once you do that, what is inside this? Okay, so this fellow has a location, let's call it 2000. What is inside is 1000. So I is an alias of j, int and of j. The address of j is stored in I. However, you will never get to see this. You can never see this. What do I mean by this? So let me give you another statement. So here is int I equals 5, int and j equals I. I've created a proper reference type j of the object I, and if I do cout less than I, less than ampersand I, less than endl, okay, and if I do the same thing with j, you can check for yourselves, the values are identical. If j had the address of something, he should have printed the address of I. He doesn't. So if this fellow shows the value 5 and let's say 1000, if this is the address of I, the second line will give you exactly identical output, 5 and 1000. It says as if I and j are same, which it is not actually. Okay. So in other words, the R value of a data of a reference type is never accessible. So now I give you the full formal definition. What is a reference type? What is a reference object? Reference object is a constant pointer. You can figure it out. To some object of who you have created. That is automatically dereferenced whenever used. So there are two properties which I have sort of quickly introduced through. A reference object is basically implemented as a constant pointer, number one, and this business of automatically dereferencing. So I should probably tell you first what is dereferencing, because I skipped that with pointers. I'll get to that now. What is automatic dereferencing? So before that, before automatic, what is dereferencing? So I have to go back to the pointer word. So here is int star p equals let's say address of I, and I assume I have already done int I equals 10. Now when you take this entity p, it's a pointer that we have noted, is a pointer to integer. It means It can only hold addresses of objects which are integers, not a float. It cannot hold that. It's illegal. So if you look at P, what all things I can do with P? What all are legal? I can do P. I can say what is P? He's supposed to give me. I can say what is address of P? He's supposed to give me. I can say what is star P? He's still supposed to give me. But this is called the dereferencing operation. Okay, so let me draw a box and clear it out. So if I did this, suppose the address of A is 1000, then in P what I have stored is basically just the value 1000. And somewhere in 1000 location, since I value is 10, this is the address of I, right? This was pointing. Address of P could be anything. Suppose it is 2000. This is the L value of. So when I say just P, what is P? P is same as the R value of P. Always. For any object, if you just call its name, it's the R value of the object. R value of the object means what is stored inside the box. This is R value. And hence, the output has to be 1000 for P. When you say give me ampersand P, you are saying where is P stored? That's 2000. I have given it here. This is L value. The only thing I have to introduce is what is star P. Now star P says dereference P. If you are only having a pointer, you can use star P. Because this is an address, I can go to the object inside the address. So extract the object from the address which is stored in P, from the address. This is a dereference, not reference, but do the reverse. So if I dereference P, I take 1000, I go to the 1000 location, pick up the value, and the returned value is 10. What if I asked here, what is I, what is address of I, and what is dereferenced of I? For this integer object I is the R value, so it will give you 10. Ampersand I is the L value, which I have said is 1000. But star I says, can you go to location 10 and fetch the value? It will not be allowed because I is not an address, it's not a pointer. So you can do dereferencing only on pointer type of values and not on normal values. Okay, so this cannot be dereferenced, it's a compile time error. So now if I come back to my previous slide to explain what I was saying, okay. So I'm going to give an example and explain this. So I've told you what is dereferencing. I have not told you what is automatic dereferencing. I'll do so immediately. And I'll also give you the feel of the constant pointer. Okay. And then you will understand the reference type, and it's a very powerful type which is extremely useful for passing values in functions. And functions are, as you know, the bread and butter of C++ like languages. So here is my reference type last explanation. Suppose int I is 15, an integer object created. I create a reference object, I'll give it a slightly different name, so ref I, and I put it equal to I. Okay, now what is happening inside, which will never be seen by you, but let me give you a feel. Here is I, R value 15, let's say L value is 3000, type is integer, I'm writing all the relevant entities. Ref I is yet another different variable, different object, so here is the name. The type is int and, everything to the left of the declaration is the type, for I it is int, ref I it is int and. The value inside I am about to show you. The address of this could be 4000, but we have said it typically stores the address of I, which is 3000. But remember, this I have said is a constant pointer. Anything that is constant, the value cannot be changed. It is a constant value. In this case, a pointer. So this is what is actually internally stored. But suppose you say, what is the address of ref I? Let's see how it processes. So when you say address of ref I, he goes to whatever is ref I. Okay. So what is ref I? Ref I happens to be this entity 3000. So 3000 is what? 3000 is dereference. So ref I is basically address of the entity which is basically holding the value of 3000. But this fellow will immediately dereference, which will say, no, no, you can't look at 3000, that's not your business. So please go to the object. Sorry, so it will turn out to ampersand of 15. Where is 15 stored? Which is 3000. So whether you do ampersand of I or you do ref I, the answer is the same. Why? Because every time you try to use ref I, it takes the constant pointer stored in there, dereferences it automatically, whether you like it or not, which means uses it to go to the object and then uses the object and does the operation. So for example, if I did ref I, this is only for declaration. I do ref I plus plus. Let's see how it works. Ref I has the value 3000. So it takes the value 3000, dereferences it to go to I, which is the value 15, okay, does plus 1 to it, which is the value 16. Supposed to store in 4000, no, dereference, so actually it stores it here. So this is the reason when you do ref I, you will never be able to see the address of ref I, you will never be able to see the pointer. Whenever you ask anything about ref I, he will show you only that of I. Address of ref I is address of I. Content of ref I is the content of I. Okay. So this is how the system has decided to implement a reference type. What is the advantage? The advantage is that you have a pointer which does not behave like a pointer because it's a constant point. So one example of this which will show the power of reference type over the power of pointer type. So here is a very standard example given almost every textbook, every instructor uses it to explain the power of reference type. I am sure most of you have seen this innocent looking functions which is called swap, meant for interchange. What does it do? It's supposed to interchange the values of variables I and j. Okay. So how do I swap the values? I introduce a temporary. So here is my TMP. Since I want to change the values of I and j, in TMP I can store any value. Let's say I put the value I. So I have saved the value of I. So I can now do I equals j. I's value is destroyed. And then I can do j equals TMP. Right? I'm sure you have seen the code. It's nothing new for you. So by using this TMP, the effect that we have done is we took some values of I and j. Suppose it was a star and this was a hash to explain two different values. At the end of the whole show, okay, the thing has converted to hash and star. We have swapped the two values. We all know that this function has no effect on the caller. So for example, if I call this function with swap x and y in some other calling context where x and y are integers, this will have no effect because only inside you have changed the value of x and y. These parameters do not carry, it's a call by value mechanism. I will not get into details, but basically the values of x and y have not changed, are unchanged. If they have changed only inside the function. If you say cout ij, they are different than I and j. But outside from the caller, there is no change. Okay, so let's do something else. I want this change to happen, so I don't want call by value. Nothing prevents me from giving two pointers. So I'll use int star I and int star j. So I now take physically two pointers of two values. So what do? I can use a TMP again. I should use a TMP, a temporary place. Now what do I do with TMP? I want to hold a value. So in TMP I can put the value of I. How do I do that? I basically take I, which is int star, and put. So this is star I. So if I do this, I take the pointer dereference and I put in the integer variable the value of I. I have dereferenced and put the value. Okay. Then what do I put in I? I have to dereference the value of j. Okay, so I have to do star of I equals star of j. So take the value of j and put it into the place where I was. And then you do star of j equals temp. Or some code like this. This affects the change visible to the outside world. How do you call this? I have to call it differently. I have to say int x comma y, and now I have to call it as address x comma address of y. This C. So many of you may know. The function definition, the call. Okay. So look at the context that is changing and how careful we, the writers of the program, will be. This is the definition, this is the use. Use ampersand here to pass pointers. Use stars here to accept pointers. Rewrite your code using pointers and objects so that the whole thing goes well. So if you want to make changes visible outside a function, I have to use earlier this in C, the world of pointers like this or something similar. Now look at what reference type will enable you. So here is my swap function written for the last time. Since I have reference type, it is int and I, int and j, the body, just like you use for call by value, int tmp, store any of the values in I, in tmp, I stored I can destroy I put equals j, and I put the value tmp. Exactly like the call by value code, the first code. Right? So much easier to write for the user. I'm not dealing with pointers. I just am using an alias I and j, and I'm swapping the value of the objects to the aliases. How do I call? Call, I write int x comma y, and I just use swap x comma y. And if you do it, you will see the values of x and y have changed. This is a feature of C++ which I have used many times in my course. I wanted to explain it to you. So how does it work? It works like this. In the callers area there are two values, x and y, right? Which are integer data type. They have some values, some integer. I don't care what the values are. When we call, at this call point, the control transfers to the caller, to the call function. But what are I and j? They are aliases. So if this is the location of I, and this is the location of j for the function swap, what will get passed here? Since these are aliases, effectively it will have the pointer or the address of x, which you will not know and I will not know. A const address of x and address. However, you know that in reference type I don't use any pointers. So when I do tmp equals I, in temporary, because of the alias, the value of x will move. I equals j, though you are using constant pointers, their dereference, this exactly works like a simple object. So we deal with objects and yet have the power of pointers. This is what reference type is all about. But we have the so all my applications that I will make of reference type of C++ is only in such things where I can pass arguments through pointers, and the only difference is that the changes to I and j, the arguments, will be visible outside the function. So I get the power of a pointer without using star. I just use ampersand in the parameter definitions. Inside I deal with them as objects I and j. But whatever original objects you pass, the aliases I and j will behave as if you are working with the originals, because implicitly you have the pointer without having the trouble to deal with the pointer notation. This in crux is the power of reference type. I have actually gone through a lot of slides. This is the point in time where I would like to break. Okay, but I'll tell you where I am. So I've covered 17, 18. Okay, the example swap is also here. Okay, this I'm going to skip for the moment. Notes on array and strings, I'll leave it for you to read. So I'll take a break from lecturing from my side, but essentially I'll take some questions if you have, and I'll continue after this. Let me fix the point. Since I don't need this immediately, I'll skip this. These are good features of C++. And I'll deal with 35, which is template functions, immediately after. the question answer session is over. Okay, so let me see what your questions are. I already see something on my, okay, so let me go in a stack order. Question from Akanksha, which says, is there any alternate option for swapping rather than using a third variable? Okay. The answer is yes, but that is very tricky code. Okay, so I don't want to advocate it as a policy, and it doesn't work for all types. For integers, it so turns out there is a very tricky solution given in the 60s, where by adding, subtracting integer variables, you can recover the value using only the original variables. But that is not a generalizable solution. So don't worry, you cannot swap two strings with it, you cannot swap two characters with it, you cannot swap two floating point variables with it, or you cannot swap two objects of your defined types. Okay, so it's not generalizable, but for integers, yes, there is a very tricky solution which is not useful for others. Okay, so I suggest use the third variable. It is cleaner code, easier for you to read the next time, easier for somebody else to read it the next time. Okay, Namisha says, what is the meaning of alias? Okay, I thought I was trying to tell you, alias is basically another name for an object. Okay, and after that the alias and the original object are used interchangeably. Okay, like Bapuji and Mahatma Gandhi. If you just say Bapuji, it could mean your father or somebody else, but typically in a use without any special context, it means Mahatma Gandhi. So Mahatma Gandhi is the original leader or the original, the great person of India, and Bapuji is his alias. Okay. So basically alias is another name given to an object which already has one name. So the first name is not an alias, the first name is the original. I hope this is clear. There is somebody, Kshitija from asked a question. Once a reference variable has been defined to refer to any particular variable, it can refer to any other variable. Okay, the answer is no. Okay, you observe I use the word constant pointer, right? So if I create an object I, and if I create a reference object or an alias by giving it some name, let's say J, then remember what is stored in J. J has the address of I. Okay, suppose the address of I is 1000, right? So it has hold 1000, and it's a constant pointer, which means the value of J cannot be changed. You can't even see it. Since it cannot be changed, J cannot reference any other object. It will keep referencing to I. But the value of I can change. Understand, right? The pointer is constant, not the value. So J's content cannot be changed, but I's content can be changed anytime you want. I think Kunal's answer is the same. A pointer is just a pointer. Or maybe I'll use my board for a short while just to explain this point, because many of you are having this doubt between. So Namisha, are you okay with my answer, or you have some more question to ask? I mean, any other doubts? So it will take a lot of time to write it out. Okay, dangling reference I have not come to, I'll take it up. Pointer, so I'm going to tell you the difference between pointer and reference type, because that is coming up again and again. So maybe I'll do this now. Okay, so you see I've created two columns, one called pointer, the other called reference. So let's see the first column, what is happening. As a result of this association or assignment, the value of P has the value, let's say 1000. 1000 is the address of I, which has some value. I don't know. Let's say the value of I is something, whatever, 10 or whatever. This is what is done by this assignment. Since I don't know the value of I am not giving you a value here. What is the consequence of this? There is no binding on the fact that P should hold on to 1000. I can write immediately P equal to address of J, and this can change to the address of J, which could be 2000. So the value of P is changeable by changing P to point to another object. Let's say the value of I was 20. There is nothing which prevents me from changing this value to 200. So the contents of both P and I can change, which means I can have a different value, and P can point to another object. Okay? P can point to any object, provided it's an integer. This is for pointers. Now let's go to references. I've done the same thing. So here is, let's say, some I which has some value. Let the address of I be 1000. Because you created a reference, here is R. This has an implicit const pointer this, and maybe its address is something 3000. I don't know. Now what is not changeable? Value of I can change. You can change it to another value. If it is 100, you can make it 1000, whatever you want. But this value is not changeable. How can you not change the value of R? Because to change the value of R, you need to know the address where R is. Okay? Only then you can change R. Where is R? Then I can go and put something in that location. But this is never shown to you. It is never visible to the user. And check it out when you have time. If you do address of R, you will get address. So I hope you can see, and we are back to both audio and video wise we are connected to you. Okay. I think I lost connection for a while. So if you can see the video slides and if you can hear me, then without my pen and paper exercise, maybe we can start. We have lost enough time. Okay. So I will cut short a little and try and go slow only over the slides because I'm not able to write and show you what I want to explain. So I request all of you to focus on slide number 36. This is exactly 1/3 of the whole lot. Slide number 36, and the heading of the slide is template functions. So I'll take about 5-7 minutes to explain this feature, hoping that you do not know this. It's a very powerful feature to have in the language of C++. So if you all have zeroed on to 36 slide, I hope you are clear. I'm trying to speak as clearly as I can, but I think my throat problem may be. So let me start explaining slide 36. See, there is a small piece of code. It isn't much C++, it's like C only. There is a function called max. It takes a floating point array. It takes the size of the array as the second argument and returns the largest floating point value in the array. Okay, the code is very elementary, so I will not go through the code. It creates a variable res and by continuous comparison fills res with the largest value, right? So why am I showing you this? Because once we have worked out with great detail how to write a function which does a certain job, in this case finding the largest value is max, okay, is the max. How much work do I have to do if I wanted to run this function max over a different data type? Say integer, say string, say an array of characters, okay, or an array of my type. Let's say my type is student's roll number and their current grade point or whatever you have. Okay, two valued pairs, anything. So I have to compute maximum over a set of values which are well known, but the type is not float. Okay. So this is what template functions are supposed to be very good at. So look at the next slide, which is slide number 37, and observe that wherever the word float was there in the previous slide, I have replaced it by a variable t, which is not defined. So if you read this function definition in English, it will say function max returns a type t, which I don't know. Its first argument is an array of name m, but array of what? Of type t, which I don't know. Second argument is an integer, so that's well stated, everything is known. The first assignment statement is creation of a variable named res assigned to the first location of the array A0, but what type? I don't know, it is t. Okay. So this is what is the abstraction that one does when one wants to figure out that the code of max is very general and needs small cosmetic changes in order to make it work for different data types. Okay, so this is the first observation, that max depends very minorly, exactly in 3 places. But if you change a different type, the function will work. But I have to rewrite it. Okay. So C++ people said, if this is the scenario where a minor rewriting, copy, paste and some correction will make a new function, please don't do it. We will do it for you. Okay, so look at slide 38 and look at the things in blue which says now template, angular bracket open, class capital T, angular bracket closed, and what I had shown on the previous slide. This is said to be writing a template function. So what is a template function? It's a specification of a function where the type has deliberately not been given. Okay. So you can write template function for min, you can write template function for sorting, okay, and a variety of other things where the code remains same and minorly changes because the object type, the value type has changed. So here is an use of a template class in the very next slide, which is 39. If you can understand this, and if you have not seen a template function before, then I'll be very happy if I can help you explain. So observe in int main, or the main function, there are 5 array declarations, each of different type. A, the first one is an integer array of 6 elements, the values are there. B is yet another integer array but with different 6 elements. CH is a character array with some 5 character constants in there in single quotes. Float is an array of 5 floating point values, and str is an array of strings, which is the way you write in C++, of 4 letters, collection of two string of length 2 consisting of alphabetic characters A to Z. Now let me explain. I'll explain 1 or 2. Take the first line. Cout in C++ says output something like printf. Printf or display minus the double quotes maximum is, and then it makes a call to a function. Okay. This is the template function defined on the previous slide. Now what is happening now? Listen to me slowly. Max A of 6 has been found to be a definition of a function max. The compiler goes and checks where is max. I go to the previous slide. It observes that there is a function max, but there is no type associated to it. It's a template function. Okay. So the compiler is going to do some work. It will take this call A comma 6. A is an integer array and 6 is an integer. It tries to match with the template function and tries to derive the value of t, the type of t. Since t is the type of the array, t is the return type, t is the rest type, and the call only has an integer, the compiler figures out that we need an integer max function. So what does it do? It uses the template, ignores this class template t, replaces t by int and creates a concrete integer function, which is int max, int array, comma int size, int res, etc. So replace t by int and you create a function which is callable, which is a concrete function, I call it. So at that point in time, max a comma 6, compiler generates a function from the template and calls it. It's an int max function. What happens when you hit the next statement? The compiler realizes it's a call to a max function for a character array and an integer second or two. Now it says, okay, where are the definitions of function max? The compiler finds out that there is an integer max function which has just been created, which does not match the character max function or the character call, but there is a template max function also. Since the integer function does not match, the compiler uses the template and then creates yet another concrete function which will be car max, car array, car res, and then calls it. So you can see what is happening. At this point max a comma 6, no concrete function. At the end of the call, one integer max function, one template function. At the end of car, two concrete functions, integer max, character max, and template max. At the end of f comma 5, since f is a floating point array, there are three concrete functions, one more for the float point created, and of course the template. At the end of str, there are four concrete functions and the template, one for string added. However, the fifth call, max b comma 6, is found out to be an integer array, and in this case the compiler says I have already created a function with a comma 6, please go and use this integer function and do not use the template. So what has actually happened? The ease on the user is that you know that you are going to use a function which is very similar, which finds max. So only please write a template function. That's all. So you write one version of max, parameterize it with a type t, one or more as required, and then jolly well, flexibly make calls like I have done, and the functions are generated and called automatically by the compiler. There is a lot of material I have given after this which talks about the pros and cons of using template functions, how it typically uses it, how it's typically generated by the compiler. So it will be nice if you read those pages, and if you have doubts you can ask me tomorrow, but I am going to skip them because they explain the power of template. So this discussion goes on till I think there is some slow processing, I will wait. I was trying to focus on slide 46, which I want you to read. Okay, so now I have got the slide number 47 ready. Since I cannot use my, I am going to go to the slides in a different order. So now I want to create something called a linked list, which I showed you right on the first few slides that I was trying to do. And instead of going through, I am going to jump to a certain slide, which is the purpose for doing all the exercise that I am doing before it. So let me go to what is the expected output when I want a linked list. There is a lot of discussion. I am going past 53, 54, 55, 56. Don't worry, I will come back to it. Even 59, and I want to be there on slide number 59. So I hope you can reach out to slide 59 and then I'll try and explain. If all of you are there. So slide 59 says linked list class design. Okay. But there is not so much of design here, it's actually a use. So this is the power of classes or object oriented programming in C++. So assuming all of you are there, let me start. It is just the main program. The entire machinery is outside this slide, which is the purpose of the slides before it. So let's say how do I use a list if I want to use it. So this is a linked list. The first one is nothing to explain, int num. Look at the next one. It says list L comma M. So someone, it is me in this particular case as a programmer, is trying to say I want to create two instances of or two objects of the type list. Some data type that has been defined, one is called L, the other is called M. So create two lists, whatever lists are, that has not been cleared here, so you wouldn't know, but two, if things are going well, two objects of type list, class list will be created. The subsequent one is the input collecting loop, while scene greater than num says I don't know how many numbers are there, please give me numbers one by one, I will collect as many as I can. So scene greater than num takes an integer, puts it wherever you want it, in this case num, and the loop enters. When there are no more numbers or when the program reaches the end of the file, then the while loop will be executed. So scene in greater than num returns a false value when no new number is found or when the end of file is found. So let's get into the while loop now. The right hand side says L dot append bracket num. What is this? This is operating on the list L, which is declared 2 lines above it. Append is a function. I'm going to tell you in English its purpose. So a list is made up by creating compartments and linking them together. The last compartment or the last element in the list has to be augmented by, increased by one more element. I want to put a new element at the end of the list. This function is supposed to take care of it. So this says, right hand side, take the list L, apply the append function which is defined by someone, and to this function I give an argument, let's say 20. In which case the value 20 will be added at the end of the list L if this function is written properly. And then this append probably is returning a new list after the change, and the same name L is used to catch it. Which means my new list after the append operation is the list L with the element added at the end. Okay. Look at the next one. It's just single line. I'm giving you long explanations. The list M is yet another list different than M. So L and M are two lists. The second statement in the body of the while says M dot insert. Please apply the insert function on the list M, and to this apply an argument, say 20. So what will happen now? 20 will be inserted to the list M. I'm going to tell you now that insert appends at the first element of the list. Insert places an element at the head of a list. So this insert function applies on the list M, takes a value, puts it at the top of the list and returns the new list. So what will happen? Orally let me explain, since my pen and paper is not working. Suppose I give two numbers, 20 and 5. First I give 20, execution of the while loop, and then I give 5. What happens to L? L appends the first number 20 at the end of the list, subsequently adds 5 at the end of the list. So in L the numbers are 20 followed by 5, right? There's the order in which the list has been populated. What happens to M? The first time you put 20, 20 goes to the top of the list, and next time you put 5, you put it again at top of the list, 20 is pushed back, 5 is put on the top. So M list has the elements in order 5 and 20. Since you can see the same numbers given in a certain order, they will be appearing reverse in insert as compared to append. That's how it is designed. If you want to find out how many elements are there in list L, because you don't know how many times while loop will execute, you can do L dot length. To apply the length function to the list, and it will tell you how many elements are there in list L. This is how it is defined. If you want the number of elements in M, do M dot length. I'll skip this merge for the moment, but this merge was supposed to concatenate two lists. Take two lists, at the end of the first list join the second list, and this thing together becomes one big list. Okay. So yeah, if I have ABC in the first list, and if I have 1, 2, 3 in the second list, then first concatenated with the second is ABC 1, 2, 3. If you concatenate the first list to the second list, the reverse order, first the second list, then you concatenate with the first list, then your list will become 1, 2, 3 followed by ABC. This is what concatenate operation does, and that is used by the symbol plus. So whoever has designed this class list has made sure that operator plus is redefined over list elements, lists. Then you observe that the last thing which I have used there or something that I have used here is a merged list Okay, I can also have a display function which can display the elements of the list and so on. So the purpose why I was telling you all this is that if you want to use interesting data structures, first think of a use for it. Okay? So if you want, let's say, a data structure for chairs for whatever reason, you want to manufacture chairs, then what you should do is first create a class called chair in the programming language sense, okay? And then you create different chairs out of it, chair objects, and decide what you want to do. So creating the factory which can produce chair is the main job. Similarly here, defining a user defined type list, which is my second line over here, is all the hard work that we need to do. How to create a list, how to define append function, how to define insert function, how to define the list function, how to display the list, how to merge two lists, how to remove an element from a list, how to find an element in a list, and so on and so forth. Lot of operations you can support. But once you do it carefully, the use is just like what I have shown you. You solve a problem by creating a list, processing the list as per your needs, and getting the job done. Okay. So many of you have asked in the past, I could see, what is the application of pointers, linked lists, and so on. So these applications are typically characterized by, defined by elements or populations that are not predictable easily. If you can predict the size of a population, maybe you can use something like an array. Okay? But if you cannot, then probably you should use something like a linked list. So let me give you a little more useful application. Suppose you are holding a conference, right, and you have invited people. There are people who will come and participate, present papers, there are guests. However, you are not sure how many people will actually come. So what do? Hoping that it's a very popular event, a big person is coming, you can book an auditorium of size 5,000 and be sure that it will be doing its job. This is like an array-like attitude or approach. The problem with this is that if only 10 people come up, then you end up paying for the auditorium of size 5,000. You pay for its AC, you pay for its all other accessories, but you utilize very little of it, right? Because your estimates went horribly wrong. In real life, you can't do much, but in the programming world, you can. So if I observe that only 10 people came, in the programming sense, I will only give him resources worth 10 people. I will not create an array of 5,000. I will use in such a way that only 5 people can come, can get processed, the problem solved, and you get away. However, even if 5 billion people came, my solution may still work. So the net story is that if I am not sure of the population size, then it is very, very difficult for us to figure out what is to be done. Looks like I have been enabled now. My paper thing is working. I'm very happy about it. So let's see if I can, cover up something because of this. So I'm trying to use it just to make sure what I was trying to say. So if you want to use a data structure, and my purpose today was to use several of them. Okay. What we were trying to do is, for example, the list itself. So I want to use list as a data structure. To be more precise, linked list. It's not just a list. So what we said we will do is, we will not worry about it. Of course, we will do something like class list, and here will be a huge thing that we will fill up to be defined. Don't worry. Okay, we don't want to solve this immediately, but I would like to see what will I do with this list. How do I solve a problem? That is more important. Okay, so I'm going to create a problem which is very useful in numerical maths, and since you wanted applications. So here are something called polynomials. I've given it as a problem later. Okay, so what are polynomials? Polynomial is something like x to the power 2000 or plus 2x to the power 50 minus 26. This could be a polynomial. If the polynomial had all the powers of x, please use an array. That's the best way to do it. But look at this polynomial. It has only 3 terms. The first term has coefficient 1, exponent 2000. The second term has coefficient 2 power 50. The third term has coefficient minus 1 and value coefficient minus 26, power of x is 0. What will people do? They'll say, of course I can use an array. Please go ahead and use an array. No issues. 0 to 2000. In the place write the coefficient. The constant term is minus 26. Please write it here. At the 50 position, the exponent value 50. Please put the value plus 2. And at the place 2000 exponent, please put the value 1. So what have I done? I have an array of size 2001 and I have 3 elements sitting in this huge place. The rest are all zeros, so the coefficients are zeros. You realize? These are sparse polynomial. And unfortunately, even though we may not like, sparse things occur in numerical problems very, very often. Sparse matrices, sparse polynomials, sparse vectors and so on in real problem solving. So now anyone who uses an array is going to end up using wasteful resources. What will a linked list fellow do? So here is one. So they will say, okay, since you have given me such a unnatural problem, I will create boxes like this. Here is my coefficient. Here is my exponent. And here is my next element. The first, if you remember, my first thing was x to the power 2000. I read it from the previous slide. Plus 2x to the power 50 minus 26. Okay. So when you insert this is what we will do. This is 1 into 2000, coefficient 1 power 2000. So here is coefficient 1.0, exponent 2000. I'll read the next term. I'll populate it with yet another box. Coefficient 2 in the same order, exponent 50, and there is yet one more element. So please go ahead. Coefficient minus 26, exponent 0, end of the list. This is my polynomial. Okay, so this is a completely different representation than what you will do with an array. And who did this? People did it long back, even before pointers and such things were available. So they said, I don't care the degree is 2000, there are 3 terms, I have only 3 places. The only extra thing that is happening is this place that you are using to create the next fellow is a waste of space which is not needed in an array. Because I need here the address of the next element. If this fellow is 2000, I want to put 2000 here. If this fellow is 4000, then I want to put 4000 here to reach this place. So this is a linked list for an application which is very real. And I have asked you in the assignment to develop something. So here is what I'll not complete it because that's an assignment. But I would like to define, depending on the application, a class polynomial. Okay. What do I do with it? So my use will be like this. Poly, maybe P1. You want to find out the degree, please do P1 dot degree. I'll give a machinery here. He'll tell you the degree of the polynomial. This will be a function. You want to find out the roots of the polynomial. Here is a function called roots defined in that class. It will give you all the roots. Okay. What else do you want? Whatever you want. You want to evaluate the polynomial at a point. Give me a point, polynomial dot eval, and give me a floating point value. I'll evaluate the polynomial and give it to you. What is the value of the polynomial? For example, at 2.0, you will get it. Whatever you want. You want to add 2 polynomials. I should be able to write P2 equals P1 plus P2. Done. Just like you do add 2 numbers, I'll add my polynomials. I can divide 2 polynomials in the same manner if you wanted to. I could also write P1 equals P2 division P3. This is the power of the polynomial as a class. So you now realize that the easy world of arrays goes away, and in this world when you write the main programs like what I have written, it looks as if polynomials are built-in types. You create polynomials, you add polynomials, you multiply polynomials, you find roots of polynomials. Okay. Polynomials are used for prediction. You can say the market rates are like this, please tell me the market for tomorrow. The polynomial will predict and give it the value to you. Let's evaluate a polynomial. So anything. So again, to characterize, since I don't have too much time, linked lists are a great facilitator, are a great tool. Once the size of your population are uncertain, they are changing, which is very often happens in the real world. Okay. For example, the amount of video frames that you are collecting, somebody who is processing videos, he doesn't know. Okay. It may be varying from few thousands to few millions, and yet you have to do the processing. What do you do? So then you use dynamic data structures, dynamic ways of processing, for which whatever this module was supposed to do is ideal. So use linked lists, don't use fixed entities, and then you proceed. So really speaking, my allotted time is up, but we have lost a lot of time in between. So I want to know from you, how long can I continue, okay, to do a little more in what I was trying to do. Maybe IIT Madras, Lavana can help me. For example, can I continue for 15 more minutes? That is the minimum fair thing to do. Otherwise, I'll have to come back tomorrow and catch up. So I'm asking for you people, I do not know your comments. So can we go on for 15 minutes or should I not? You can continue. Okay. So I'll continue for so there are a lot of questions. Let me take the questions before I do anything again. So what is the dangling reference? Okay. So this is something, if people know pointers, then it makes a lot of sense. Okay. The dangling reference is basically, what is a pointer? Let me go back. I not use my thing. So when you set pointer to an object, okay, typically these pointers are, which I have not told you, are not defined from the static part of memory, but we get memory at runtime. Which means that I do not say how many elements will be there. I start with an empty collection. The first person arrives, I say from somewhere, give me one object, enough space to hold one object. That's called dynamic memory. If you know the word heap, they are allocated from that heap. So I get a place, I get a room, I note down the room number, which is basically the address, the pointer, and I continue. Just like you get memory at runtime, you can also return memory at runtime. So when you check out of a hotel, you surrender the keys to the reception, right? And you walk away because you returned. Now what if you walk out of the hostel, but you keep, or the hotel, but they keep the key with you? Now it's possible that there is only one hotel with the name and the key, and therefore you can identify. But the point is, once you have left the city and the hotel and it's just the number 103 written on it, you just won't know what it is. This is an instance of a dangling reference. So I have an address in memory, but it does not point to the object that I was using it to save. So again I repeat shortly, a pointer is an address of an object in memory in which I have kept some useful stuff. But after I return the stuff to the heap, I don't have any use for it. But if I don't destroy that pointer, then it becomes a dangling reference. So I'm referring to an address in which something is staying which is not belonging to me because I've surrendered that stuff. So dangling reference, dangling pointers are unsafe if you don't allocate and deallocate memory properly. So the point is, if you deallocate an object, if you return the object, please also return along with its address. Don't keep its address saved somewhere. Please return that also. That's a fair thing to do. Sparse matrices, don't worry, I'm going to do it tomorrow. So you will have no issues with it. A little bit of sparse matrix I will do. So what is a sparse matrix? A matrix in which lot of zero elements are there. So therefore you don't want to use a 2D array, but you want to use a linked list like representation. It's very interesting. Actually sparse matrix I'll do in module 2 as a non-linear data structure. But I can give you some reference tomorrow, some idea tomorrow. Okay. And sparse matrices are of course in most branches of engineering very often found, and they are a major pain if the matrix size is big but the elements are small. Question from Bharti: what is the effect of merge 1 equal to L plus L? Okay, so this I can explain it by just drawing a simple diagram. What is the purpose? Okay, so the statement was something like merge equal to L plus L. It was not 1 plus 1, remember, it is L plus L. Okay. What does it mean? Now I'll draw. Suppose your L was, let's say, an array of characters. So A followed by maybe semicolon, single character, followed by, let's say, dollar, and followed by, this is my null, which means it's end of the list. Okay. So this is a short form for saying please concatenate L with itself. So what will it do? See, this is L. It will create yet another instance of L. So here is A, here is semicolon, here is dollar, it's yet another L. There are two L's here, happens. Then it connects them. So this is append, connects the end of the first L to the start of the next L. Okay. And then it returns this merge list by giving it a name, merge. This is the left hand side. So the first L, concatenate, this is plus, with the next L. Any two lists can be concatenated. I have connected the list to itself, and this is named merge. So what is L? L still points here. L is still holding on to the original list. So this is basically telling you that once I create lists as first class citizens, I can do a lot of operations on them, and this is a short form for saying join the first list with the second list. This is the right hand side. Okay. It so happens that both lists are same, that is by accident, and the final output of this operation is assigned to merge, and then assign it to a new list called merge. Okay. And you can write such powerful statements not only here but even for polynomials. That's what I said. You can do P1 equals P2 plus P3 in some sense. So the two polynomials will be added, the appropriate coefficient exponent match will be done, and your result will be taken care of. Okay, so in the remaining 5-10 minutes that I have, I'll do a little bit, I'll do it only on my paper out here, and I'll ask you to read the slides, because otherwise it will become very slow. Is that active? Oh. So what I was trying to do after my list was there, which you can read up now, I was trying to do it I was trying to give you 3 data structures. One is list, okay, the other was a stack, and the third was a queue. I am supposed to continue doing them even tomorrow when I'll do some applications along with your help. Okay, I hope you can see what I'm writing. Okay, so I have some questions, but I'll answer them at the end. So list I have already shown you. A list is basically a collection like this, where you have to go from the first element to the last element. Okay. A stack, since I'm going to do only linked allocations, will look something like this. Okay. So this is the top of a stack. A queue, on the other hand, the one which I am going to use is a little different than what you may find in some other places. I'm going to explain it through examples. Okay. Typically a queue is like this. This is called the front of a queue, and this is called the rear end or the other end of the queue. For a stack, which is this is my stack. All operations are done at this end, which I was explaining the last time. For a queue, the front is used for deletion, to delete elements, and rear is used to insert elements. And you observe that these are all linked. I am not using arrays. So linked lists were basically, okay, the linked list class will be very easy for us to be used. So I'll first develop a linked list class, which examples are given on these slides. Have a look at it. And then I was supposed to develop the stack and queue if enough time was given. But still I want to take you through some of the elements of creating a stack and a queue. Okay, the conceptual issues of a linked stack and a linked queue. So very briefly. So a linked stack or a linked queue. Okay. Let me take up the linked queue, which is conceptually easier. So what I said there are two elements, front, okay. You have the element which is called a rear, which are two pointers to the queue, and then you have a collection, a linked list. Depending on how many elements, collection of elements, which is basically a linked list. Okay. Now observe this small conceptual interesting thing which people again discovered long back. They said, why two pointers? We can do with only one pointer in the case of a queue. So I'm going to only discuss that solution. So suppose I'm going to build it up for you. So suppose I have elements 2, 13, 15, 7 joining a queue. Okay. So don't worry about the implementation right now. I want to just form a queue with those 4 elements. How do I start? I start with an empty linked list. So my queue has, I have to put it, my queue has the address 0 or null. There is no element. This shows an empty queue. Okay. My first element 2 joins. This is what will happen. Now my queue has, okay, the queue was empty. I'm going to show you. So here is 2 coming in here. Now 2 may have more elements. I must keep a space for it. I'm going to use a circular list. 2 points to itself. Okay. And what does Q point to? Q points to, so how do I reach this? So I note down the address of 2 and put it in Q. So this is 1000, let 1000 be in Q. So to reach the queue, I take the address, go to the element, and I get to the rear end of it. I'll talk about that later. So basically I'm keeping only the rear of the queue or the rear pointer of the queue with me, and I have disposed of the front. I don't want to know who is at top of the queue, who is in front of the queue. I just want to know who is at the last element of the queue. Next comes 13. So here is my 2 already there. Okay, and my pointer is here. So what I do is I take the next element, I create and say, okay, here is the place for 13 who has just joined, the recent fellow. I again make it circular. After 13 comes 2. And my pointer is to the rear. So here is my queue pointer. I note down the address of 13. Okay, let me continue. The next time when 15 also joins the queue, I have 2 here. The next element to come was 15 last time. This time 15 has come. The next element to 15 is 2 back, and I only know the address of this element, which is 15, which is the last element in the queue. Okay. So why is this enough? Because observe that what is 2? 2 is basically the next element to 15. It so happens that rear, if this is the rear, then this arrow, the next field, if you want to call this value as next, is always the front. This is the front, because the list is circular. Who is next to the last element? The fellow who came in first has to be. Okay, so I have accessed indirectly to the first element. I don't need the first element. I don't need a separate pointer to the front of the queue. And since a queue does only inserts and deletes, I can do an insert by whatever I was doing. For example, from here I was inserting. So what I did, I took the current pointer. I first created a new element by placing it here. Then I connected it to the last element. Okay, I made it point to the previous element by knowing where this fellow was pointing to, and changed the rear to the new element. 2 or 3 pointer operations. So this is basically in CS notation a constant time algorithm, O of 1. 2 or 3 pointer operations, and I have added an element at the front, at the rear of the queue. How do I delete? How do I delete the front element? The first fellow is to be serviced, 2 has to go. It's even easier. Take the last fellow, which is the rear. This next you take away, and this fellow next you short circuit here. So deletion is even more easier, right? So both the insertion and deletion are O of 1. So it turns out that a circular list as a queue with a pointer to the center of the queue does all the job that two pointers can do otherwise. So this is a conceptual issue, nothing to do with the implementation, array or a link. Similarly, at the conceptual stage, if you want to create a linked list, stack in the form of a linked list, so what we do is we create a top and put it to null. I'm going to create a linked list, stack in the form of a linked list. List is a stack of strings. Now I want to add this string which is language C to it, double quote C. So what do? I create an element, I put the value C prime prime there or whatever, C or whatever you want, the name of the language, put a 0, change my top to point to this is 2000, please put 2000 here. This was all obtained at runtime. So really speaking, if you want to know, this whole stack will develop on the heap, whereas the static area of the program is what it will be there. Typically this will be on the stack of, not the stack I'm implementing, but the stack allocated by the compiler. Okay, in some other area, let's say it's a static area. Let me not confuse you. Next time we want to push the language C++. I've already pushed C. Now I want to push C++ to this collection. So what do? This is already there. I use a new place from the heap. I have to ask, initialize this to C++. Stack always notes the recent element. So this I connect first to this by copying this value, one pointer assignment. Okay, then I delete this. And this new element which I've added, I point here. And my stack has grown by one size. Okay, so when I do this, if this is 3000, then this changes its value to 3000. So two pointer assignments and my stack has increased in size 1. One to connect the new element to the previous top of the stack, and then I change the new top of the stack to the current element. And the stack can grow. So you observe that both push and pop operation on a stack are very easily manageable, just like the arrays on a linked list. So this is the stack as a linked list. I have the address of the top element on the stack and I can process it the way you want. So on the slides I've given you a lot more details, lot more code which will implement the same things in a certain way. So what I suggest is, before I start tomorrow, okay, I'll take the questions now. Before I start tomorrow, please read up the notes which are in lecture 2 and come up with your questions if you want. You can put the questions before I join here at 2, so I can come and see the questions, answer them to the best I can, okay, and then I'll continue with the applications of the material. So read, if you have doubt with the code, ask. If you have doubt with the design, ask, or whatever else that you feel you are not comfortable with. Okay, so now I'll take up whatever questions I can find before I stop. I have a question from Manoj Kumar Yadav. Which one is faster and why, a linked list or an array? Okay, so this answer is given to some extent in the slide of lecture 3. That is why I begin with, I compare an array with a linked list. But it's not easy to answer this question in a context independent manner. Okay. So instead of saying which is faster, a linked list or an array, I would suggest you take an application, whatever you have. Let us implement it both using a linked list or an array, and then see for that application whether it is faster or not. So in general, if you want me to answer, I'll still try and give you some. If you know the size of an array properly, then a lot of things are possible. So creating an array is easy, it takes space. Accessing any element of the array is directly constant. Suppose I create an array of 1 million, whether you access A0 or you access 1 million minus 1, the last element, the computer takes roughly the same time. There is no difference between accessing the first, the middle or the last element of an array. What about the linked list? The first element is instantaneous. One dereference from the head you get there. How do you reach the 1 millionth element? I have to run down this collection 1 million times. Hugely slow. Okay. What if you want to insert and delete linked list? I can do it very quickly. I can insert at the top constant time. I don't care how many elements. If you want to insert at the back, you can do some extra manipulation and do it quickly. Insert and delete in an array, really speaking, is not possible. Let's say I have an array of size 100, my array is full and I have to insert an element in the middle of the array. You cannot do it unless you create a larger array at runtime, copy your old array into that, then insert and do it. So array collection for insert and delete is very unsuitable when the array is getting. So it's very slow to insert and delete, but it's very fast to access. Linked list is very fast if you want to run down the list searching for something, because it's a sequential collection, but insert and deletes are pretty fast. So if you ask the question which one is faster, we cannot answer. But if you say I have a linked list, I have an array, I want to do this operation, name it, we can answer which is faster. So accessing in arrays is faster, linked list is slow, insert in linked list is faster, in arrays could be very slow. Delete in an array physically is very complicated. If you want to delete an element, you have to copy the rest of the elements up or down, which is very expensive. In linked list, it is sometimes very easy. Okay, so I would say when you want to put a question like this, you have to say which operation and then you get a definite answer. Which is better than that. Okay, I'll close here. Okay, sorry for the intermittent technical problems, but I think in the end we were treated properly. So please be ready with your questions when we meet tomorrow at the same time at 2 p.m. Let me try and address as many questions as I can, and then I'll go on with mostly with application development rather than looking at these data structures after they are cleared up. Thank you.